Right, so today we're going to talk about psychoacoustics and its effect on how we code media. So psychoacoustics is basically the study of psychology alongside acoustics. It's got a physiological aspect, so the actual structure and shape and size of things within our body, and it also has obviously a psychological aspect. So some of it there is psychology and how the brain kind of interprets the signals that it's sent. So we're here to try and answer this question. So how can we decide which information in an audio file cannot be heard? So we can determine a bunch of stuff that's inside an audio file that cannot be heard, and we're studying audio obviously because of psychoacoustics as a focus this week. If we can decide which parts of an audio file we can't hear, well, that's a pretty good candidate for something that we can throw away. And so that's what we're trying to aim to do here. We're trying to throw away information that we cannot hear in order to try and preserve and assign the highest quality or the highest number of bits to the parts of the audio we can hear. Now, that's a bit of a giveaway, and here it's kind of talking about a bit more broadly about lossy compression as a whole. So we are looking at lossy compression, the idea that we can lose information. Again, we have to decide how to do that. How we can hear things is obviously how we've decided to do that in this particular one, because we're talking about psychoacoustics here. But there are two models that we can adopt, in terms of what we might want to do. So the source model looks at the source of the content that we're trying to encode. So it will look at the content and it will say, right, well, there are speech elements here. So maybe we can encode speech instead of encoding audio itself. Maybe there's specific codecs that we can employ. There are a few around, specifically around, voice over IP uses these kind of things quite a lot. Specific codecs that will encode the voice. So there's one called Speaks, which I remember from TeamSpeak back in the day. TeamSpeak was a kind of gaming VoIP server that you could fire up, and it had a list of codecs as its option. One of them was Speaks, which is a specific voice encoder. So those things are optimized highly for speech because speech has certain features. Now those codecs were particularly poor for music, obviously, because they aren't designed to do that. So for an MP3, again, kind of giving the game away here, for something that is going to essentially code any audio, we might be inclined to try and choose something that relies on the receiver model instead. So we can basically model human hearing, model perception, and if we can find some features there that we can use to find redundancies within our audio, then brilliant, So that's the use of the receiver model. So that's what we're going to focus on today. Now, our ears themselves are obviously adapted over the evolutionary term. And we've talked in the past in classes about the fact that our speech and our hearing have kind of co-evolved in order for us to be able to hear speech particularly well. And we've talked about the idea that our sort of hearing response in particular frequencies is tuned for the speech frequencies, essentially. So evolution has adapted and adapted us and optimized us, but it's also adapted and optimized us for more things than just speech. This is quite a complicated area of study. So it's not just the frequency response, there's also other things there. We are selective in our hearing. There are particular things that we focus on. We have the ability to solve what we call the cocktail party problem, which is a completely unsolved issue, actually, in terms of acoustics and psychoacoustics, as far as my knowledge goes. Which is essentially, if you're in a busy room with lots of talking going on, if you look at someone or you're focusing on a particular area of speech, it doesn't actually have to be visually based. Visually helps, and the visual element helps when you're looking at people talking. Their speech patterns themselves do obviously help. But when you are looking or focusing on somebody's speech, in a crowded room with lots of speech going on, a human is able to kind of isolate one track, one person, even among lots of speech. Now, computers are unable to do that. When you get an AI model to try and track in and focus on a particular person in a very speech-dense environment or a speech-dense audio track, they can't do it. And if you're trying to use things like text-to-speech, they are particularly poor at being able to isolate out one person and draw that out and turning it into text. If you do any experimentation in this, you'll find this, right? So it's always really hard to get speech to text to work very well, you have to have a very good signal to noise ratio in order for that to work. So we've got this magic stuff that happens in our psychoanalysis, in our acoustic psychoanalysis, our psychoacoustic system, that allows us to do that. And it's a bit of a mystery how that happens. It's obviously a brain thing, but there's also physiological things as well. So there are physiological adaptations, the way that our basilar membrane actually responds to sound and how it kind of like picks up sounds in different frequencies and parts of it that are excited and ignored and all that kind of stuff all comes into this. And again, it's a very complicated issue. So there's some physiological. So physiological is the physical thing. Psychological is the bit that's happening and based on processing and the brain stuff. And it's a bit more black box and a bit more interesting to study in lots of ways, but also very difficult. And the selection pressure that we have as humans is to optimize for attentiveness and speech. Now, when we talk about evolution, and when I talk about evolution, I'm obviously kind of interested in it, and I always try to point out the fact that evolution doesn't happen without some kind of selection pressure. So selection pressure is basically something that is pressuring your cohort, your group, into evolving for some reason. People often think of evolution just kind of happening, like it's something that rumbles on in the background and organisms improve over time. And that's true, but they do not improve, and they actually get worse and worse over time if there's nothing killing them. Or if there's nothing stopping them from reproducing, basically. So selection pressure is something that is pressuring your cohort into not reproducing unless they adapt. And you've got to wonder what that is then. If we look at the ear and how that's come together and look at the ear's kind of response, well, it wouldn't happen unless there was some sort of selection pressure there. So the selection pressure, by kind of guesswork here, is obviously to optimize for attentiveness, probably to avoid predators and things like that. Maybe it's to focus in on catching prey because we are hunter species. Perhaps it's to optimize for talking to each other, social cues and finding a mate and all that kind of stuff. All that stuff's really important, obviously. So we optimize for those things. We've got selection pressure that's optimizing for those particular things, and it's affected our speech system. So now let's try and find some redundancies within audio. We have the idea of frequency optimization. Now, naturally, if we have a file with a bunch of sound on it, and that sound isn't in a particular frequency band, then it's quite tempting to say, right, well, we can probably just bin off that band in some way then, right? So if we can filter our audio down into some way that we can get the different frequency bands out of it, and we can choose an area of the frequency where there's no real information, maybe we can just bin all that information, and that's quite useful. As we've studied in digital audio, we tend to do this with, when we sample audio, we do it in sort of the PCM method, so sampled audio. We take a bunch of samples and we string them all in a line, and that describes our audio. So we obviously did need to do some processing here in order to bring out different frequencies, but we need to find some that we can focus on and bin off information that's not there. Now the example I've got here is obviously a very contrived one. I've taken some pink noise and, well, it's actually white noise because it looks more even on one of these spectrograms, and I have binned off an entire section of it. It would obviously never look that, that's an unnatural thing, but it's just an example. So that entire chunk of the spectrum, I've just sacked it off, and you can clearly see there's a bit missing there. And for you and I, if we were just trying to sort of use our intuition to design a coding system, there's no reason to try and encode an area in which there's no audio. So we can focus on it less, and we can assign it, a different amount of bits. We can focus on less bits, basically. So we can obviously do this in some way. Now let's think about how this comes together. We know this about our frequency response. We know this chart. I told you right back in, I think it was the first week I saw you guys, that you're going to see this a lot, and I described it as the map of the human hearing. Just to recap on it, the top is obviously the threshold of pain. It's how loud sounds need to be for them to be kind of uncomfortable. Right down at the bottom is our threshold of hearing, so the very quietest sounds that we can possibly hear. And in between there, you've got like lots of curves that describes how effective you are at different frequencies. Now, when you are listening to a sound file, you might have it turned up particularly loud. Now let's for instance say that it's right up at the top there, right up at the top, so it's kind of around this area at the top here. So you've got it loud enough that you are basically getting towards the threshold of pain. Now there will be sounds still that are quiet within that file, and those sounds might fall below that bottom red line. Even if you've got it turned up really loudly, it doesn't necessarily mean all the sounds are loud, because we have dynamic range within our sound files, right? So there are points at which that are loud, and we have points that are not so loud. So the first principle here is that we can bin off all the stuff that is lower than our threshold of hearing. And that's kind of where we are with this, right? So if we can find sounds that are very low in our, with a very low amplitude, we can essentially get rid of those. So we know this about our hearing, and we can actually use this to our advantage. Now here, in the next slide here, bam, we can actually codify this or make it into something that we can actually map into what we call the standard audibility model. So for any given MP3 or again sound file that we're dealing with, there's going to be an inaudible region, and we can kind of map that. We can say, look, there's a whole chunk of stuff here that there's no chance of us ever really being able to hear. So by default, let's just zero all that out and not listen to it, yeah? And we'll see how we do that in a minute. It's not quite as easy as getting rid of it necessarily, but you assign less bits to it, essentially. You assign it less information. So this is our standard audibility model. So by default, if we are frequency optimizing an audio file, we can just make the admission that we can get rid of everything that's below that line there and say, look, we can't hear that, let's not focus on it, let's not attribute data to it. And if you look at that entire thing there, there's a third of it really. Not to say that we have sound completely evenly across this entire thing, but generally speaking, there's a third of it there. And there might be a lot of redundant information in that file. A third of it might have a lot of information that we can just kind of get rid of. Now, the person mixing, and we often think about the person kind of mixing these tracks and how they want it to sound and all that kind of stuff. This is incidental information, really. This isn't something that your engineer is really hearing. So it's tempting to think, well, we don't want to code this way. We don't want a lossy code because it's not the way the engineer that mixed the track wanted us to hear it. And it's kind of true, but the thing that you're actually getting is not what they wanted you to hear. They are giving you incidental information that's behind the track that even they can't hear in the studio, most likely. This is the kind of level of small, low level, low amplitude information, generally speaking, nobody can hear. So we're not really losing anything. And this is the key. This is why we use the acoustic model. We're trying to bin off information that we can't actually hear ourselves. So we've got this threshold of audibility. We've got an audible region. We've got an inaudible region. Now, the way our basilar membrane works, and if you remember, the basilar membrane is the membrane that's inside the ear that responds to different frequencies. Up and down that basilar membrane, we've got different chunks, essentially. And as we've kind of established in the past, they're logarithmic in the way that they come together. We've got logarithmic style hearing, which means that a small change in the low frequencies feels like a large change in the high frequencies. They feel equivalent. So this is codified or put together by some work from a guy called, I think his name was something Bark. It comes to this thing's called the Bark scale. And essentially it breaks these things down. And again, we saw this last term into this thing called the Bark scale, which breaks the frequency spectrum of our hearing down into sections, into chunks. Now, what we've not really studied in this degree yet is the physiology of the ear. Like, we haven't really talked about what happens with those hair cells on the basilar membrane. We've talked about the fact they wiggle, right? But what's really happening is a sound will excite a specific part of your basilar membrane, yes, but it will also excite areas around it too. It's not a perfect, you're not getting a huge spike in one place and nothing else. So if you picture the basilar membrane, I probably should have put this on the slide in some pictorial manner, but if you picture the basilar membrane and you go up and down it, when you send a sound down it, it will excite a specific area the most. So there will be a specific peak, and your ear will say, well, that's that frequency then, great. But it will also mess about with and excite areas around that too. So it's not a perfect spike in one spot, it's kind of a curve. And so this dot here on this chart, again, I stole this from YouTube. I'll put the YouTube video up on the Sol page, so you can actually look at this video, because it's actually quite good. There are areas that he misses and stuff like that around it, though, so obviously this is still a very useful thing to know. But the diagrams are nicer than anything else I found in books and things. So here you can see that what we got, around about sort of 1,000 hertz or something, you've got a dot. And that dot is obviously your ear's interpretation. That's the frequency at which this sound happens. Either side of that, though, you'll have less energy, but still some wobble happening in the bands next to it. And then even less than that, you'll still have some wobble happening in the bands next to that. And then again, less than that as you go further and further out. So there are still bits and bobs that are happening in your, down your basilar membrane when a particular frequency is stimulated. So even a pure tone of a specific frequency will still kind of annoy all the basilar membrane areas around it. So that's quite useful to know, because yes, it annoys those areas, but your brain doesn't really give you all that information. It doesn't say, oh, that 1K tone sounds like a smear, surrounding 1K above and below it a whole bunch, and it's all a bit of a mess. What it says to it is that's a 1K tone. So it's ignoring a bunch of like drama that's happening around it. So there's a 1 kilohertz tone and then a bunch of schmutz that's kind of happening around it, and your brain kind of disinterprets it, doesn't mind about it, ignores it. That ignoring, though, is very useful to us. So you've got action happening there, but your brain is ignoring it. We can take advantage of that. So the presence of a tone being there causes a raising of the audibility threshold. Remember we talked about this audibility threshold back here? We've got this threshold of audibility, which basically says that if we pass down below it, we can't hear sounds. Well, look, we've actually adapted that now. And this diagram here is okay. You can see you've got a 1K tone there, which is represented by that spike. And you can see the energy of that tone is not perfectly, spiky, but it's fairly spiky. And then there's this kind of dotted line, or this line here that goes along, and you can see it raises the threshold of audibility. So by default, we not only have our base audibility threshold, we also have a threshold that we can adjust up and down depending on what is happening in our track. So we can temporarily raise that threshold, essentially. So that's what it looks like. I said this diagram is kind of mid. It's hard to see a little bit, and there's lots of dotted lines and stuff. So I kind of like this one a little bit better, right? So in this one, you can see that there have been a bunch of frequencies identified, and they are given to you by those crosses and circles. And those crosses and circles have got cones underneath them. And that's basically the area of the frequency spectrum that is affected by that particular frequency. So the area of the frequency spectrum, if these are pure tones, again, this example may or may not be pure tones. You've got stuff that's happening in the frequency spectrum that is not necessarily pure, but just to give easy examples, we give these pure tones. And so here you can see you've got these examples, and then underneath you've got these cones of area that your ear essentially can't hear anymore. So it cannot hear those particular frequencies because they're so close to a loud frequency, essentially. And the basilar membrane is kind of trying its best to ignore, or the brain and the membrane together are trying its best to ignore that particular stuff. So those cones are inaudible, and so we can basically map those or squeeze them all together, turn them into a curve, which is essentially what's happening there, and that's our new curve of inaudibility, essentially, underneath there. So that raises, and that gives us this idea of spectral masking. So spectral masking is essentially the idea that if you have a loud or have a particular frequency that's relatively loud, it will mask frequencies next to it, and you can't hear them. Now, how does this come down to reducing data, right? So we've looked again in the past about the idea that we can reduce the bits, and I gave you an example last year, in fact, of a music track that was sampled at 8 kilohertz, in 8-bit. So it was a 44.1 kilohertz sampled audio track, and we kind of established the idea that 8-bit, the common wisdom is that 8-bit is going to sound terrible, but actually 8 bits is plenty enough for a track that's not very dynamic, so it doesn't have much dynamic range. So here you can see we've got our kind of threshold of inaudibility that's mapped over the top of our track, and it happens to track along. We've basically gone through the track here It's analysis of the whole track, which wouldn't really happen with codecs. We do it over windows of time. But anyway, just to keep the examples clear, we've gone over the track here. We've made this threshold audibility chart. And then we can basically overlay what it would be like if we did the whole track or resampled the whole track in various bit depths. So we've got 3 bits here, which is the yellow one, which is hard to see. We've got 5 bits, which gives us less noise, and we've got 7 bits, which gives us less noise again. So these curves here are the background noise, essentially. Now, we might be tempted to think that 3 bits is quite bad because we can hear all the noise in the low frequencies there. I keep touching the screen. We can hear all the bits in the low frequencies there, and that's kind of bad, right? Because we're going to hear those noisy bits there. And that's totally true. So 3 bits is kind of out the window. 5 bits is almost acceptable, but there are areas, especially in the low frequencies, where there's not a lot of energy that's masking the noise away, where we will hear it. So here you can see the orange line kind of peaks above the black line a little bit, and that means that we'd hear that noise. Now, 7 bits is kind of plenty for this particular track. So 7 bits is fine. So we can encode this whole thing in 7 bits and pretty much get away with it and not hear any noise. We not hear the hiss or the harmonic noise in the background. But again, we are looking on the frequency spectrum, though. We're looking for spectral redundancy. And therefore, using this concept of spectral masking, we could say, actually, from around about 1 kilohertz upwards, we could get away with 3 bits, which essentially more than halves the amount of data that's going into representing that audio. So we more than half it. The rest of the low frequency stuff there, where there's not a lot of sound pressure actually, and you're more likely to hear the noise because it's not being masked away, essentially we can keep at 7 bits. And then again, we're not getting into the details of this necessarily, but using Fourier transforms, we can take chunks of audio, we can separate it out into the frequencies, and then we can assign different bit depths to different frequencies. So the high frequencies here, we would assign 3 bits. So because there's a lot of noise happening there and it masks the noisiness in the background, the spectral masking. And in the low frequencies, we could assign perhaps 5, maybe 7, just to be sure. But again, clearly we're getting quite good gains here. We used to have an entire track here that was probably sampled at 16-bit if it was a CD, and we're taking it into MP3 again, for instance, and saving, going from 16-bit to an average of around about probably 4 or 5 bits. So some of it's 7, some of it's 3. Obviously, you have to take an average to see what the average bit rate is. So massive savings. And again, MP3 can give you like 11-to-1 savings. So if that basically means our WAV file will be 11 times bigger. And it can be audibly imperceptible as well. And again, because of these modeling techniques, that's why we can get away with such low bit rates. But yeah, you can put one in front of somebody and the other in front of somebody and they can't tell the difference, no matter how snobby people are about MP3. Now finally, there is another thing that we can use, another technique. And again, we can explore this again in just a moment when we look at our seminar session for this week. But we can look at the idea of temporal masking as well. And again, this is similar in the sense that now we understand how spectral masking works. We've got the basilar membrane that's all excited and stuff's going on. If you think about what happens in time now instead of frequency, in time you have the basilar membrane hair cells, wiggling about and doing their thing. And then after that, they will kind of die down and still be wiggly kind of thing and disappear off. But your brain has to interpret the sound as having stopped. So it kind of does its best, once the kind of amplitude of the wiggle dies down a little bit, to cancel that stuff. So when we have a sound coming in, relatively loud sound for the sake of clarity here, you have a masking sound that comes in, so a sound is happening on the basilar membrane. And it will wiggle your hair cells a bunch, and then those hair cells will kind of take some time to stop wiggling, but your brain needs to say, right, well, the sound has gone. So the brain kind of cancels out that last bit, the kind of decay time after the sound stops. Otherwise, we'd hear it, and it wouldn't really represent reality. So what happens there is there's masking. So your brain is doing the best to ignore a sound, and this is across the frequency spectrum. If a loud sound happens and then stops, your brain kind of cancels everything that happens immediately after that sound in order to get that decay time to really tighten up. So that allows us to have an area then that we call temporal masking. So we've got post-masking happening. A loud sound happens, and then after that, we lose a bit of the ability to hear, essentially, anything that's happening. And that gives us a window of area that we can reduce data further. Now, what's really interesting about this, and again, this is something where understanding in this world is not perfect because it becomes very black box and brain driven, is that you also get an element of pre-masking there as well. So sound will enter your ear and it will wobble your basilar membrane and it will start to get those excited. But then if a louder sound comes along, your brain kind of just goes, oh, never mind about that little bit that happened before. And again, that kind of happens at sort of in the region of 25 to 30 to 50 kind of milliseconds. Again, this happens differently depending on people. This is a very biological process, so these numbers will change person to person. But a certain amount of time there, you end up with pre-masking. You can actually just delete everything that's happening in your MP3 file, all the samples, get rid. And after that, 200 to 300, like sort of between 200 and 300 milliseconds on this chart here, you end up with this area of post-masking, which is a much longer period and much more useful, in fact. But both are there and both are useful. So temporally, we can delete stuff, get rid of stuff. And that, again, is super useful. So those are the major techniques within MP3. And this is the way that this all comes together, right? Now, you will see, again, this whenever you see these block diagrams, I've seen a few of them. They're very hard to understand because they kind of use these terms. A lot of academia and the way this stuff is studied is kind of gatekeepy. They want you to find it difficult to understand, essentially. But the reason I put this up is because you can see here that there's stuff that we can recognize. The FFT we know about, Fourier transform, we can turn things from time-based into frequency-based. You know, we can look at things in the frequency domain, and that's exactly what's happening in MP3. We've got our psychoacoustic model. That's everything we've been talking about today. There's some interesting stuff that's happening there then above that we don't really understand. A polyphase filter bank and MDCT. So there's a DCT, which stands for direct cosine transform, that we're going to get into a little bit later on. And then quantization, non-uniform quantization. Now we know about quantization because quantization is us choosing those bit depths and choosing where those samples land according to our bit depths, the length of a word. So non-uniform probably means that we don't do it the same across the whole track, right? We do it differently for different frequency parts, and that's what that means. And then the last bit, that's the bit that's actually we've been talking about here with the psychoacoustics. We reintroduced this idea of a lossless coding. So Huffman coding is used in MP3. As I kind of said last week, we kind of use that as a freebie. If we can get rid of data without losing anything and then be able to reconstruct it on the other side using something like a Huffman coding scheme, then why not? So we do. So MP3 also contains lossless encoding too. And then we've got this coding of side information and then bitstream formatting, CRC word generation, so cyclic redundancy coding. Again, we've not gone through that now. So there's a bit of extra stuff here that we're not necessarily understanding. But the key tenets of MP3 are temporal masking and spectral masking. And so this technique is useful for us to take an 11 megabyte wave file and turn it into a 1 megabyte MP3. And this is how culturally the kind of digital music revolution came about. Now, a lot of this is attributed to Apple and the iPod and all that kind of stuff. And yes, that is true. They kind of popularized it by making it kind of sexy. But before that, we also had MP3 players. They were beginning to get popular. Quite popular by the time the iPod came out. And again, Apple have got this kind of annoying habit of doing something the same as everybody else, but just sexy enough to make it interesting. We have the same thing with like technologies like AirDrop and FaceTime and the iPod and all that kind of stuff. Even the iPad wasn't necessarily a new idea. It was just a refinement. They do things well enough to make it popular, essentially. So they are attributed to a lot of this. And they do use MP3. You can use MP3 with iPods all the way back from, I think, the second or first generation. But they also use another encoding standard called AAC, which we're going to take a look at later on down the line here. So it takes these concepts and expands them a little bit more for a little bit of extra saving for your coding scheme. So even better than we've looked at up until now, but also manages to make it higher quality too. Cool. So that's it for today. Thank you very much for listening.